I'm Riwei. I'm from City University of Hong Kong. I'm very happy to present our work in ATC. The title of our paper is SolFS, an operation not versioning file system for hash-free efficient mobile cloud backup. Uh, this is the outline of our paper. It involves our problem in background and motivation and the SolFS details in the design and the implementation session. We also have the evaluation session to show the advantage and overhead analysis in compared with the original file system. So let's get into the first session, the background and the motivation. And mobile cloud backup are widely employed on existing mobile devices for different purposes. It usually involves the vendor built-in cloud backup applications such as Oppo, Huawei, and Xiaomi, and the third-party mobile cloud backup applications such as Dropbox and OneDrive. They are used for different purposes, such as the data security and to save the storage space. And built-in applications are usually for the smartphone snapshot. And the one important thing in a cloud backup is their frequency, because in our mobile device there are many personal data. If we want to keep data security of this timely data, such as the financial data, business document, as the desktop version of OneDrive and the Dropbox, they will do immediate synchronization once the file is modified. So this is very important to keep the data security. So the frequency is important. So there's a daily for high performance mobile cloud backup solution for mobile devices. But existing cloud backup application on mobile devices have some limitation. For example, if we use the direct synchronization scheme, it directly upload the file data to the cloud server. For large files, even with some slightly modifications, it still need to upload the whole file. It will introduce many high-level traffic, of course, but their CPU overhead is relatively lower. And if we use the delta synchronization, it will, of course, it can reduce the level traffic, but it will increase the CPU usage because there are many intensive hash computation, and the computation will lead to high CPU usage, and the CPU usage will drain the battery to reduce the time we use the phone, and the CPU usage used for resources used for the mobile cloud backup will compete with the user application. Imagine that if we play a mobile game on my phone and there in the background there was some data synchronization is performing, of course the user experience will be significantly affected. So we also conduct some experiments. The results show that hashing operation will introduce over 170% execution latency and very high CPU energy consumption. So our goal is to, of course, upload the modified data only like the data synchronization, but without expensive hashing. For this goal, our insight is that if we can check all the modified range of a file since the last backup, we could directly upload the modified range of data only without hash computation, because we already checked the modified history of this file. We can know where the file is modified, so we can accurately find out this data and load them. So this is our insight. Therefore, file system is a suitable component to achieve this insight and goal. But after deeply investigation, getting the existing file system techniques, especially the file versioning techniques, I found that some file versioning techniques like the copy on write approach, such as the referring feature in XFS and BTFS, because the file versioning techniques allows us to manage different versions of data, just like the figure shown in the left side. So we can classify the old data and the new data, and then we can upload the new data only. So it can somehow achieve our insight and goal. But these techniques have some limitation. The first one is that The copy on write approach will result in a file fragmentation issue. It will result and then degrading the sequential read performance, like the figure show at the rightmost side. And it also requires change the file system layout of the existing mobile file system. It is very impractical to change unpopular mobile file system. And another approach is to do undo logging for file versioning. This approach used in the Wayback Netflix, but this design does not incur file fragmentation overhead, but it has to store and manage multiple versions of file data, result in high storage overhead. This is the common issue of some file versioning techniques because they were targeted to do versioning for file data instead of their logs, instead of their file modifier range. So this is the existing limitation. So we can conclude that existing file system techniques are unsuitable for efficient and low overhead mobile backup. Okay, our solution for this limitation is operation log versioning file system, or for SolFS for short. The SolFS have 4 major design goals. The first one is hash-free identification. It means that we can identify the newly modified range of file without hashing, and then we can return this modified range to the cloud backup application so that it can accurately to find out the file data and upload the file data to the cloud. And the second point is the overhead minimization. It means that SolFS does not introduce additional file fragmentation issue, and our design will try to minimize the memory and storage overhead. And for another 2 design points, they are proposed for practical consideration. For example, the granularity aims to support multiple cloud backups and multiple versions, multiple backup progress. And the backward compatibility aims to support existing mobile device so that we can allow them direct upgrade without changing the file system layout. Let's see the architecture of the SolFS. SolFS involves 3 primary design points. The first point is the provider mergeable operation logging. This logging design aims to check the modified file data range of each file via operation log. The operation log means the log of each wise offset and length to this file to a file. So with this log, we can check all the modified range of this file since last backup. So this is the core design of the SolFS. And the second point is the mlog versioning. The mlog versioning allows me to manage the file difference between 2 backup, and especially when there are many different cloud backup applications running in the same smartphones. We can use mlog version to accurately classify the different backup progress of different mobile cloud backup application without interfering each other. And the last one is the hash-free delta synchronization. With the previous 2 design points, this allows SolFS to calculate a file modified data range without hashing. We can combine them to as a tree and return to the cloud backup application so that it can directly upload the data in file data without the hashing. Okay, let's see the first design point, provide mergeable operation logging. We can call mlogging for short. The mlogging, firstly, will have in-memory mergeable operation log tree. This log tree is to manage and store file operation log. When user perform a while operation to this file, we will create operation log or mlog for short and then insert into this in-memory extend tree. The extend tree allows me to merge the continuous mlogs together to reduce the additional storage and memory overhead. And the second point is the persistence with the compact mlog, because if we want to check all the history in memory. But once the device is reboot, all the history will be will lost. So that we need to persist the M.log tree of each file's M.log tree to the disk to ensure that the M.log tree works after the device reboots. So this is very important to do the continuous tracking of each file. But to further reduce the storage overhead for the persistency, we use a compact form of the M.log. The core idea is that if the offset, the number of the offset and length is small, we can use less storage space to store them, and we design just like this figure. We design a simple compact form of M.log to reduce the storage overhead. And the last one is the dynamic granularity alignment. I mean, because the M.logs indicates the file offset, Y offset, and the length, but it does not indicate their units. So their units can be different. We can let an M.log to be a bilevel unit or picture level unit. And if we increase the bilevel units to the picture level units, of course, the M.log will be significantly reduced. But this is the trade-off. It means that we can not very accurately to upload the file data in picture level, and also we design a simple trapsoul to do this conversion. The second major design point is the M.log versioning. The M.log versioning it means that because there are multiple car backup, and each car backup indicates M.log history. So we need to use these M.logs to use these M.logs based on their versions. So we store different version car backups version in ILOs, and then we form them as a version ILO chain, so that we can have version ILO chain to indicate the backup history of this file, and then based on this design, we perform the backup driven versioning. When we have a new backup, we can create a new ILO and insert this new ILO to the ILO chain. It means that we already conduct a new backup, and all the M.logs received after this backup are stored in this new inserted ILO, so that we can check the file modification after since the last backup. So this is the core idea of the backup driven versioning. The workflow, just like this feature, is simply insert a new ILO into it and receive a new M.logs here. And based on this design, we can classify different M.logs between two backup. So this is the purpose of the M.log versioning. And the last one is the hash-free data synchronization. We also have the mergeable operation log tree, and we have M.log versioning, so that given a version number, we can know we can combine, we can traverse the ILO version chain and merge all the M.logs during this train, so that we introduce the collaborative version management. It means that it is different from the traditional data synchronization. It is trained Chun list to find out the difference between the local device and the remote server. In our design, we use a version number to represent instead of the Chun checksum list. So the version if the version number of the local device is different from the cloud server, we can obtain their version difference, and then so we have a small version number and higher small number, and then we can check the M.log stores in the version ILOs of the corresponding M.log between these two corresponding version number, and then combine them as an integrated to a file extension tree, just like this one. We have this M.log, M.logs, and finally combined to the modified range like this one, and return to the cloud backup application. And then the cloud backup application can upload this data to the cloud server without any hash computation. So So that we can eliminate the computation overhead of the traditional data synchronization techniques. Okay, let's see the evaluation. Our evaluation is conducted on a Pixel 8 with Android 14 and Linux 4.15. The remote cloud server platform is running on a Intel platform with a Ubuntu 20.0. So this is a simple setting. We compare with 3 baselines. The first baseline is hash sync. It means that we will chunking a file into different chunks and calculate the MD5 of each chunk and exchange the chunk list between the local device and the remote server and upload the modified chunks. And the hash sync and the WebR2 sync plus will do Boolean injection to find out some inserted data of the to further reduce the level of traffic. But the difference is that async do the Boolean injection on the local device side, and the web to async do the Boolean injection on the remote server side. Let's see the first results, the cloud synchronization time compared with existing solution. SolFS reduced the same time by around 88% on average in random updates. This is due to the hash-free design, mitigate the intensive hash computation overhead. And in the level traffic, SolFS shows remarkable low level traffic compared with existing solution due to 2 reasons. SolFS transmits version number for backup, and it does not require transmitting the churn list. That is related to the file size. So SolFS can reduce the overhead level traffic of the churn list. And additionally, SolFS can accurately upload the data in byte level instead of churn level data of previous solution. It means that if we modify 32 bytes, we only need to upload 32 bytes instead of a chunk. Normally it is 2 megabytes or 4 KB megabytes. It is very large, and we can see the sync time breakdown. SolFS outperforms other approach by significantly reducing the hash computation overhead on both the client and server sides. That is 92% on average. The software overhead, the client server contribution, just like the number shown below. This number want to show that as the network bandwidth goes, especially we have high speed level in home and high speed level in high speed level in 6G or 7G, the emerging level technology. Computation on both the client and server side lead to the significant software overhead becoming a bottleneck. So SolFS mitigate this issue by minimizing the hash computation. For the mobile application workload, it improves 7% of the 70% of the sync time and the 70% of CPU usage. So it works for practical workloads. For the overhead analysis, by replaying some application operation chase, it only leads to around 6% read and write performance loss due to the compared with the original mobile file system, and additional around 500 kilobytes additional memory consumption. So it is very effective and no overhead. This is my report about SolFS. We identify the dilemma of a mobile cloud backup. We indicate that the checking file operation officer and lens can adjust the dilemma, and we decide SolFS and we evaluate SolFS to show its improvement, and we also do the overhead analysis to show that it does not introduce significant overhead. Thanks a lot for your listening. Thank you.